Today, we're going to explore electrode potentials in electrochemistry. An electrode potential is the voltage established at the interface between a metal and an electrolyte solution when a redox equilibrium is established. Let's start with a simple example. When a metal is placed in a solution containing its ions, a redox equilibrium is established. This equilibrium can be represented by the half reaction. Metal yields metal ions plus electrons. To compare the electrode potentials of different metals, we define standard electrode potentials, which are measured under standard conditions. All solutes at 1 molar concentration, gases at 1 atmosphere pressure, and at a temperature of 25 degrees Celsius. The reference point for all electrode potentials is the standard hydrogen electrode, or SHE, which is assigned a potential of exactly 0 volts. Let's look at some examples of standard electrode potentials. In electrochemistry tables, you'll find the standard reduction potentials for many half reactions. For example, the copper 2 plus to copper half reaction has a standard potential of positive 0.34 volts, while the zinc 2 plus to zinc half reaction has a standard potential of negative 0.76 volts. Now, let's discuss what these values actually mean. A positive electrode potential indicates that the species has a stronger tendency to be reduced or gain electrons compared to the hydrogen electrode. Conversely, a negative electrode potential means the species is less willing to be reduced and more willing to be oxidized or lose electrons compared to hydrogen. When conditions deviate from standard, we use the Nernst equation to calculate the actual electrode potential. The Nernst equation relates the actual electrode potential to the standard potential, accounting for the actual concentrations or pressures of the reactants and products. The equation is E equals E naught minus RT over NF times the natural logarithm of Q, where Q is the reaction quotient. At 25 degrees Celsius, this simplifies to E equals E naught minus 0.05916 over N times the log of Q. Now, let's apply what we've learned to calculate the voltage of a galvanic cell. A galvanic cell consists of 2 half cells, an anode where oxidation occurs, and a cathode where reduction occurs. Here's a zinc-copper galvanic cell, also known as a Daniell cell. The cell voltage is calculated as E cell equals E cathode minus E anode. Let's work through a specific example using our zinc-copper cell. We have the copper half cell with a standard potential of positive 0.34 volts, and the zinc half cell with a standard potential of negative 0.76 volts. In our cell, copper is the cathode, where reduction occurs, and zinc is the anode, where oxidation occurs. So, E cell equals E cathode minus E anode, which is positive 0.34 minus negative 0.76, giving us positive 1.10 volts. And that's the essence of electrode potentials in electrochemistry. To summarize, electrode potentials quantify the tendency of a species to gain or lose electrons. The standard hydrogen electrode serves as our reference point with 0 volts. Positive potentials indicate a stronger tendency to be reduced. Negative potentials indicate a stronger tendency to be oxidized. And for non-standard conditions, we use the Nernst equation to calculate the actual potential. Understanding electrode potentials is crucial for predicting and explaining the behavior of electrochemical cells, which are fundamental to batteries, corrosion processes, and many other applications in chemistry and engineering.